Video 14-1 Dilutions, Dissociation, Ionization, Strong and Weak Electrolyte, Precipitation Reaction, and Net Ionic Equations. So, looking at chapter 14. Okay, so first thing, we have two terms here. Okay, dissociation and ionization. Now, what's the difference between them? Okay. If you have an ionic compound and it dissolves into water, it dissociates. Be careful with this one. Ionic compounds do not ionize, they dissociate. Okay. So what happens? It basically breaks up into ions. Okay. So an example, something like sodium sulfate, put it in the water, it breaks up into sodium ions and sulfate ions. AQ again, you know, means aqueous. Okay. And balance it out. Two sodiums with the two sodiums. Okay. If you have a molecular compound and when you dissolve it into water, it will ionize. Okay. If it forms ions. Okay. And you saw this earlier in the last chapter. In order for a molecular compound to form ions, it has to undergo a reaction with the water. Okay. So an example, something like ammonia. Okay. Remember ammonia? When you put H2O, when you combine it with H2O, it goes into the water and it actually reacts with the water molecule. Okay, what happens here? The H from the water, an H plus, breaks off, joins off with NH3, you get NH4 ions, and when you lose an H plus from the water, you end up with hydroxide. Okay, so an ionic compound has to react with water. Okay, now, strong and weak electrolytes. What's the difference between these two things? Okay, strong and weak does not refer to concentrations. If you have a strong electrolyte, that does mean you have a lot of it. Okay, you can have concentrated weak electrolytes or dilute strong electrolyte solutions. Okay, so what's the difference? If it's a strong electrolyte, whatever you put into water, all of it or almost all of it that gets dissolved, and it has to be dissolved, will turn into ions. If it's a weak electrolyte, you can still put a large amount of stuff in there, but only a small amount, a small percentage of whatever is dissolved will actually turn into ions. The rest will exist as neutral molecules. So if it's a weak electrolyte, it had to start out as a molecular compound that got dissolved into water. Okay, and only a little bit of the molecules will actually react with water. Okay. All ionic compounds, doesn't matter if they dissolve a lot or dissolve a little, by definition they are always going to be strong electrolytes because the only way AB can dissolve, if this is an ionic compound, is all of it has to turn into A plus and B minus. Okay? If it's still stuck together to AB and this is an ionic compound, it's not going to dissolve. But whatever did dissolve, all of it turned into ions. Okay? The only way it can dissolve is it has to break up if it's an ionic compound. Okay. Weak electrolytes, they have to be molecular compounds. Okay. And again, just because it's molecular doesn't mean it's an electrolyte. It has to actually react with water and produce ions. Okay. So it has to be pretty soluble, readily dissolve into water, but only a small percentage of the molecules will actually ionize. So what we do is we draw a double arrow like this. Okay, so it shows that you establish an equilibrium. Now, which side is favored? In other words, which side do you have more of? By definition, if it's weak, that means most of the HF that you have still exists as HF molecules. So only a small amount of it will break up into H3O plus and F minus. Okay, so in your solution, you would have floating around in here a lot of HF molecules. Okay, you can dissolve a lot of it in there. A lot of it will exist as HF. It doesn't break up. A little bit turns into H3O plus because it reacted with water, and then you'll get an equal amount of F minus. Okay, so only a little bit of those. So it's a weak electrolyte because most of the HF just stays as the molecule. Okay, so the equilibrium, when it's balanced, when it reaches equilibrium, you get a lot of HF and only a little bit of the stuff on the right side. Okay, next thing, precipitation reactions. Okay, complete these double replacement reactions. So stop the video, break it up, and then come back and check on it. Okay, so what happens is you actually get no reaction in this one. Okay, question is why? You may have said, well, I broke it up and I got compounds. Why is it no reaction? Okay, the possible products from this when you break it up, you get K plus, NO3 minus, and the strontium hydroxide is Sr2 plus and OH minus. When you split the things up and you mix the Sr with the NO3 and the K plus with the OH, you should get these products here. Okay, so why is it no reaction? Simple. When you have ionic compounds, at least one of them has to be a precipitate. Okay, remember, precipitate is something that separates out a solution because it is not soluble. Okay, so because all the things you started with, the KNO3 is soluble, strontium hydroxide is soluble. The new products, KOH and the strontium nitrate, all of them are soluble, so they all exist as ions. No precipitate or molecular substance formed, so basically nothing happened. You started out with 1, 2, 3, 4 ions. These still break up and stay separated as those 1, 2, 3, 4 ions. So nothing stuck together, nothing happened, no reaction. Okay. Now, how do you know if you're supposed to get a precipitate or not? Okay. You got to memorize the table, 14-1 on page 427. Or, oops, there's another table later on in your notes and also in this that you might find easier to memorize. Okay. Now, net ionic equations. Okay. AgNO3, NaCl. What happens? Okay, break it up. Well, we're going to break it up. You know you have to break it up into ions. So AgNO3 breaks up into Ag plus, NO3 minus, NaCl gives you Na plus, Cl minus. Okay, possible products, AgCl, NaNO3. Now, is one of these a precipitate? Okay, go check the chart. Stop the video, come back. Okay, you should have noticed that one of these is a precipitate. The AgCl actually is listed as a precipitate. NaNO3, remember, any of the nitrate compounds will never ever be a precipitate, so it always exists as the ions. Okay, now the net ionic equation shows only the ions that actually produce the precipitate. Okay, this would be the overall ionic equation. What exists as ions, this exists as ions, this exists as ions. The products, that exists as ions, so it's still as ions. Okay. The net ionic shows you only the things that produce the precipitate. In other words, you can just simply say, look, I got nitrate on the left and nitrate on the right of the arrow. I cross them out. I got Na on the left and Na on the right of the arrow. I cross those out. Okay, so what's left over is your net equation. Okay. Ag plus Cl minus gives you AgCl. Okay, in other words, what were the ions that made up the precipitate? And that's it. Okay, spectator ions. These are ions that were present when you started, and they're also present when you end. So they did nothing. They just hung out, and they're spectators. They're just hanging out, watching what was going on. Okay, so the spectator ions are the ones that are still present as reactants. In other words, they're the ones that you crossed out. So the NO3 is on the left and NO3 is on the right side. And also Na plus and Na plus. So those are the two spectator ions. Okay, so you can memorize the chart or memorize this table. Okay, you may find this one easier. Notice all soluble compounds are with sodium. No matter what the anion is, it's always going to be soluble. Same with potassium, ammonium, nitrate compounds. Okay, your chlorides are almost always soluble except for these three. Okay, and the PbCl is soluble in hot water. In cold water, it's not soluble. Okay, sulfates usually going to be soluble unless it's barium sulfate, strontium, or lead 2 sulfate. Okay. Carbonate, usually insoluble unless you combine it with potassium, ammonium, or sodium. Okay. If you had ammonium carbonate, the soluble always wins out with the insoluble. So those would be soluble. Okay. Now, the activity that you guys are doing on the lab, dilutions. Okay. And we kind of talked about this on the last chapter, introduced it. Okay. So from last chapter, you know, if you take a solution and you dilute it, you change the volume, you change the concentration, but the number of moles of solute that are in there stays constant. Okay? And if you remove part of a solution, the moles remove because it's a homogeneous solution. Whatever you remove is directly proportional to the volume that's removed. So if you pour off 1/3 of the volume, you pour off 1/3 of the moles. Okay, so this is basically what you guys are going to have to do, and you have to do it individually. How do you make a set amount of a solution that has a specific concentration, but your only source of the solute is a more concentrated solution? Okay, and we call this one the stock solution. So, how can you prepare exactly 50 mLs? And you can't go make more than 50. You can't say, oh, I'll make a liter and then just take 50 of it. You have to make only 50 mLs. The solution's concentration has to be 0.350 molar. You're using lithium nitrate as a solute, but you don't have any sodium lithium nitrate. Your only source of it is you have a big container of 2.50 molar lithium nitrate solution. Okay, so you cannot simply just go say, oh, I'll just go take a whole bunch of water, dilute all of that 2.45 molar stock solution, and then only take 50 mLs of it. Okay, you cannot destroy the stock solution. Okay, so what you need to do is take out some of that 2.5 molar solution, add water to it until the final volume is up to 50 mLs. Okay, so the question is, how much do I remove? How much of the stock solution do I have to use? And how much water do I have to add to it? Okay, so we know, because I know the molarity and the volume of the final solution, I know how many moles of lithium nitrate need to be in the new solution. Okay, remember, moles is equal to molarity times liters. Okay, and also remember this formula. The number of moles you have in your container before you dilute it will be equal to the number of moles in the container after you dilute it. Okay, so moles is equal to molarity times liters. Molarity before times the liters before you dilute it has to equal molarity after times the liters after you dilute it. Okay, so what are you trying to solve for? Well, I know what the molarity needs to be after I dilute it. I know what the final volume of the solution has to be. I know what the molarity of the solution is before I dilute it. This is the stock solution. Okay, so I am basically trying to figure out how much of the stock solution to use. It's this one right here. Okay, now once you know this, then what? Well, answer the question. How do you make the solution? Okay, if I just take out this amount, the concentration is exactly the same as the stock solution. I didn't do anything to it. Okay, so how much of the stock solution and how much water do you have to add to it? Okay, so the basic idea. This is your stock solution. You took it out of the stock solution and you put it in this pipette here. Okay, so you have your stock solution. It's in here. You figure out how much to add to it. You're going to dump it into this container. Then you're going to add water to it. Okay, when do you stop? When the final volume gets up to the volume that you want. In this case, it's 500 mLs. In our case, we only wanted 50 mLs, so we'd have to have a container that measured exactly 50 mLs. Okay, the concentration of this before you add it is still the concentration of the stock solution. Once you add the water to it, now this whole thing will have the concentration of your new solution. Okay, so let's go back and do the problem. How do you prepare exactly 50 mLs of the 0.35 molar lithium nitrate solution if you have only the 2.50 molar stock solution. Okay, so we're doing M1 times L1 is going to equal M2 times L2. Okay, this is the new solution that we're making. This is the stuff that's coming from the stock solution. Pay attention, write out all these things, do it exactly as I show you. Okay, so identify what things do we know. Okay, and then come back to this video if you need to, because you all are going to have to do this problem individually by yourself, make the solutions, and then show them to me. Okay, so what do we know? Stock solution, we know the concentration, M1 is 2.50 molar. Okay, we know that the new solution has to have a concentration of 0.350 molar. Okay, now, which one is going to be L2? The new solution has to have a final volume of 50 mLs. Notice L stands for liters, but because L is on both sides of the equation, I can still do it in milliliters. So 50.0 mLs. Okay, so I'm solving for L1. Okay, rearrange the equation. L1 is equal to M2 times L2 over M1. Okay, plug in your numbers with the units. 0.350 molar times the volume, 50.0 mLs, divide by my molarity, 1, 2.50 molar. Notice my units will cancel out, and my final units will be in milliliters. Okay, plug that in, and you should come out with 7.00. Okay, 7.00 mLs. Now, what is this? Answer the question. Remember, we found the volume of stock solution. So I need 7.00 mLs of the stock solution, which is the, this is the stock solution, 2.50 molar solution. Okay, now I need to make the solution. So I have to add water to it. So how much water do I need to add to it? The final volume is 50. So I need 43.00 mLs of H2O to add to it. Then when you dilute this solution with the 43 mLs, the final solution will have a concentration of 0.350. Okay, here's your review question. Which is the net ionic equation for that reaction?